Okay. So much like a blind person reads Braille by feeling with their finger, AFM uses a physical probe to map the topography or some other surface property of a material sample. As the name implies, AFM relies on the distance dependence of the forces acting between an ultrafine tip of the scan probe and the sample surface at separation distances of about 0.1 to 10 nanometers to profile the surface. The tip is supported on a flexible micron-sized cantilever that acts as both the force sensor and the force actuator. The force is detected by measuring the vertical bending or deflection of the cantilever, which can be thought of as a Hookean spring, where the magnitude of the interaction force F between the probe tip and sample surface depends on the spring constant K, or stiffness of the cantilever, and the probe sample separation distance Z. Forces between the probe tip and the sample are sensed to keep the distance between the tip and sample constant as the probe is scanned over, let's say, low spots or elevated protrusions on the surface. As the tip moves up and down on the surface, the cantilever bends, and this deflection is tracked by reflecting a laser beam off of the back of the cantilever onto a position-sensitive photodetector. The left-hand side is a scheme of the principal hardware components of AFM, which include a probe to interact with the surface and also to sense and transduce the interaction force, a piezoelectric tube scanner to move the sample underneath the tip in the X, Y, and Z directions with a precision of better than 1 angstrom. At discrete points in the XY raster scan, a value for the interaction of the probe with the sample is recorded to generate a 3-dimensional grid of data points that are typically displayed as a false color image. A Z feedback loop is needed to track this tip sample interaction in the Z or vertical direction, and to keep this interaction constant by moving the sample either away or towards the tip throughout the raster scan in response to variations in the sample topography or some other property. There's a 4-quadrant position-sensitive photodetector to track the vertical deflection of the scanned across the sample surface, of course, a laser source, and finally, an electronic controller. AFM can be run using 3 modes of operation. The first mode is the contact mode, where the tip is in continuous hard contact with the sample surface during the entire raster scan. The tip sample separation distance is less than a few angstroms, and we are in the repulsive regime of the force distance curve shown in the previous slide. Then we have the intermittent contact mode, where an oscillating probe is brought close to the surface of the sample so that at the end of its oscillation cycle, it taps or hits the surface. The tip sample interaction force here will oscillate between the attractive regime when the tip is off the surface and the repulsive regime when it hits the surface. This mode minimizes the lateral shear forces that are present in contact mode and is the mode of choice for imaging soft deformable materials. And finally, we have the non-contact mode, where the probe is oscillated, but at a smaller amplitude than in intermittent contact mode, so that it doesn't touch the surface at the bottom of its travel in a given cycle. The tip sample interaction force here remains in the attractive regime and is very low, of the order of piconewton. The bibliographic map on the left shows the diverse areas of applications of AFM as a characterization or measurement technique. These applications include mechanical properties, adhesion, adsorption, the growth and fabrication of structures, and nanocomposites, to name just a few. AFM is commonly used as a metrology tool to characterize the surface topography and roughness, but also to determine the particle size and step size. AFM can be used to determine the surface coverage of a component on the surface of a material sample for film thickness measurements, label-free mapping of chemical heterogeneity, and mapping of mechanical, electrical, and magnetic properties. The bibliographic map shows the increasing use of AFM to map the mechanical properties of material samples. And the reasons for this are the following. First, it's the nanometer lateral resolution of AFM. Its mapping speed, which is orders of magnitude faster than that possible using a nanoindenter. And finally, because quantitative nanomechanical information can be obtained for samples ranging from soft organic materials, where the elastic modulus is of the order of 1 kilopascals, to hard metals, where here the elastic modulus is more of the order of 100 gigapascals. In AFM, a complete force distance curve is acquired and analyzed in real time at each contact point in the raster scan to simultaneously generate images or maps of the surface topography or height, modulus, adhesion, deformation, and dissipation, as shown here for a phase-separated polymer blend. Uncertainty in AFM is related to the accuracy of the measured surface feature dimensions, that is the height, the width, and the shape. So the accuracy of AFM data is principally determined by the calibration of the piezoelectric scanner, which is the positioning and translational component in AFM, the tip radius and geometry, where these can lead to what's called tip convolution effects when the tip radius is larger than the size of the features to be profiled. And finally, the applied or loading force, as shown by the bottom images, where the left-hand side image is acquired at a lower applied force and therefore resolves the spherical features that are present on the surface of this oxygen plasma treated sample. And the right-hand side image acquired at higher force shows a poorly resolved flattened features. So what is the outlook for AFM going forward? First is the increasing use of AFM for multi-parametric imaging, where notably nanomechanical, but also electrical properties of a sample surface are directly correlated with its topography, as shown here for a graphene sample. Another technology, recently developed technology that is increasingly being exploited is that of fast scanning or video rate AFM, which circumvents the slow imaging speed and low temporal resolution of conventional AFM stemming from its serial pixel-to-pixel data acquisition. Fast scanning AFM provides image capture rates up to 20 milliseconds per frame compared to minutes per frame in conventional AFM. And so fast scanning AFM allows the real-time visualization of dynamic, molecular or biomolecular processes, but also in the case of static samples, the ability to analyze thousands of images for meaningful statistics, such as the example presented in the overview for a drug formulation study. Finally, we have AFM IR that combines the high spatial resolution of AFM with the chemical characterization and compositional imaging capabilities of traditional IR spectroscopy. The microscopic mechanism enabling AFM IR is shown in the top left-hand side. The local thermal expansion that occurs when the incident IR radiation matches the material absorption bands, excites the cantilever response, which can be used then to generate an absorption spectrum. By mapping the cantilever oscillation at a wavelength that is characteristic of a given chemical functional group, one can map its distribution on the surface. So in conclusion, I hope that I've convinced you that AFM is more than just a high resolution surface profilometer. It enables the characterization of tribological, mechanical, electrical, and magnetic properties on the nanoscale. It has broad capabilities and the ability to image samples under various conditions, including electrochemical environments and under temperature control. AFM IR enables the chemical and compositional analyses with lateral resolution of less than 10 nanometers, and fast scanning AFM finally enables the real-time imaging of nanoscale phenomena and dynamic processes on the millisecond timescale. Thank you for your attention.
Thank you, Antonella. Do we have any questions from the audience? I don't see anyone. I do have a question.
Yes.
I was wondering, how hard is the probe, the tip on the cantilever? Like, what's the material? Because like, I imagine that
usually,
when you're working...
So both the tip and the cantilever are made of the same material. It's either silicon nitride or silicon. The cantilever itself is very thin, of the order of 0.6 to 1 micrometer. And so by varying the dimensions of the cantilever and even the shape, so sometimes you have rectangular, other time you have a triangular or V-shaped cantilevers, one can produce probes or cantilevers with spring constants ranging from, let's say, 0.06 all the way up to 10 newtons per meter. So something that's ultra flexible when you need to image soft biological samples, to something very hard when you're imaging conductors or semiconductors. So you can really tune the spring constant of your probe depending on the nature of the sample. And the tip radius is of the order, it's typically less than 10 nanometers.
Okay, thank you very much. Okay, Professor Suarez, would you like to introduce the next speaker? We cannot hear you. I'm sorry. You're muted.
Yes, I am indeed. Thank you. So welcome everybody to the afternoon session. We are happy to see you here again. And it's my pleasure to introduce our next speaker, Claure Lunardi from the University of Brasilia in Brazil. And we'll be talking about Zeta potential. Welcome.
Thank you. Let's see if I can share my...
There is a green button.
Yeah, we have an... Oh, I can't share it. Just a second again. Today it's nothing working very well. Sorry for that.
Some days are like that. It's fine. We have a bit of time, so we're in good shape.
Let's see if it works now. Okay, so let's go to the beginning.
Perfect.
So you were able to see it now?
Yeah.
Yes, perfect.
Oh, sorry for that. Okay, now we are on. First of all, I'd like to thank you for the opportunity to talk to you guys today about the work that we did together with Fellipy, Jacob, Gregory, and Anderson. And I've also would like to thank the committee to choose us for this presentation. So I will close my camera, so I think it's gonna be, I don't know which one I see. Okay, hope it works. So the highlights of this presentation are the same of the one that we used in the published paper. So for Zeta potation, it's a very good technique for stability of nanoformulations. We're gonna talk a little bit about applications, limitations, source of errors, and perspectives. Zeta potation, or ZP, you're gonna see during the presentation, it's used to express, it's very used to express the stability of colloidal system. Briefly, it's the measurement, not of the charge of the particle itself, but it's the measurement of the boundary between the star layer that it's really rigid of the particle in solution, and the shear or slippening plane in the solution. So let's see if we can take the laser pointer. Okay. So the Zeta potation actually is the it's the potation that we can measure in this boundary. So it's very useful, as I told you, for colloidal stability, and it's a simple and quick measurement. So the setup for the experiment in the Zeta potation, you have an equipment with a laser beam, with a laser source, that the beam goes to the sample, and after some optical compensation and the detector, you can have your signal, and then you have the Zeta potation data. This type of measurement, it's done using a folded capillary cell that has electrodes in the cell, and a capillary where we add the sample. After the voltage it's applied in the electrodes, we can have the electrophoretic mobility measurement, and using this equation, the system is able to give us the Zeta potential data. So in 2019, one of the applications, one of the search for applications of this technique, it's we find more than 4,000 documents that contains Zeta potation term. And after we did the VOSViewer bibliometric concurrence map of all these keywords, we were able to find mostly these 4 clusters. And the main topics of these clusters are oil industry in terms of application, heavy oil recovery, rheological properties, fluids, mineral processing. The main area of the Zeta potation is in the nanoparticle polymers, drug delivery systems area, and also it's been found in environmental remediation. So the setup, the quickly one is following all these steps. First of all, you have to have your sample preparation, and before you start your measurements, you have to turn the equipment 30 minutes at least before the use to have it stabilized. You have to use a clean cuvette, load the sample, make at least 5 times measurements. So all of these are in the setup of the software setup of the measurements. And the point that it's very tricky, it's when, or interesting, it's when you have your data finally analyzed by the software. If you find this image of the green target showing you that you have a good measurement. So you can go ahead and try to understand what are the results that you got. However, if you have this alert symbol, it means that you have a poor measurement of your sample. So to overcome these poor measurements, you have to think about what can be the source of errors and the limitations of techniques that maybe you are not paying enough attention during your measurements. So the limitations, we can say there are the nanoparticles concentration, nanoparticle size, pH, type of the chemistry of this suspension that you are analyzing, and some source of errors are the applied voltage, electrode blackening or degradation, dust in the sample, cell types, and cleaning and disposability. So quickly, I'm going to talk a little bit about each one of these limitations and source of errors, so we can have a panel about what can be the source of these errors during your measurement. So the nanoparticle size and zeta potentials are quite close in terms of the influence on uncertainty in terms of the zeta data values. So depending on the size of your particle, if you have a particle or a colloidal system that is a large one, you will have a great probability to have clusters or sedimentation or even deposits of these particles in your solution. So you won't be able to get a really good zeta potential measurement. So one of the good tips to work with zeta analysis is try to know the size of your sample. So if you perform Abdallah's measurement, most of the equipment has the DLS measurement on it, so you can have the size of your sample, and knowing this range in terms of size, you'll be able to get the concentration that we'll have at minimum and maximum for the measurement. Another point that it's interesting or very important in terms of the zeta potential measurements is the isoelectric point. So depending on the range of the pH that the isoelectric point is reached in your sample, this point should be avoided for zeta potential, because when you have this isoelectric point, your emulsion can be phase separated, or you can have your suspensions become agglomerated. So that's one good example on this figure when we have the zeta potential versus the silica nanoparticle over a range of pH. And as we can see, as far as we get from this isoelectric point, the zeta potential it's more correct, and probably the particles are more stable. Another example, it's a protocol that we performed in this paper. It's the use of it's the knowledge of the fact that over the time the size of the particles can change. So when we look at this image or this picture, we can see that in black we have the time 0, and it shows us the size of the nanoparticle. In this case, it was 100% anatase titanium dioxide nanoparticles, we can see that it's a monodispersive and after that, over the time, we can have the aggregation and becoming more wide this image. So one of the consequences of this is that if you take a long time to take the measurements of the sample, maybe you don't have the same zeta potential because your sample already is not the same as before. So this is a good example to understand when the solution is stable in terms of long term of conditioning or use. Another important information is when we look to electrophoretic mobility versus ionic strength. In this case, we used 80-20 anatase and rutyl titanium dioxide nanoparticles. And we can see for both systems that when we increase the ionic strength using sodium chloride, we can see that it becomes more aggregated and it's more difficult than the particles to have the mobility in the solution. So also it's another factor that we have to take in mind when we are using zeta potential for measurements, the zeta potential, and this can be one of the uncertainty. And in terms of uncertainty, there's a rule of thumb that people used to say that, oh, if you get more or less 20 millivolts, you have a stable system, then that's the magic number. So there's no magic number because it depends on the chemistry and the type of the material that you are analyzing during the zeta potential. Of course, each one has a range that we can use more or less for predict stability, but you have to still make the measurements and take in mind that depending on the chemistry, like if it's a metal salts, if it's a metal oxide or polymers or oil in water emulsion, you have different zeta values for stability. So in terms of source of errors, we can take a look in the applied voltage. Since zeta potential is related to electrophoretic mobility and by the equations, every time we change the applied voltage and increase this applied voltage, as an effect, we have an increase in the temperature in this point of the solution during the electrophoretic measurement. So one thing that we have to have in mind, if you want to maximize the quality of the data, you have to take care when you are changing the applied voltage during this measurement. And however, on the other hand, for example, when you have a cell culture medium, it's already well known that you have to apply low voltage because it will prevent the medium degradation. One effect that is quite common, and it's a sort of error, is the electrode blackening. As you can see in the pictures, you depending if you use an organic solvent, you can damage the capillarity of the cell. If you use samples that have dyes or can deposit some metallic materials in the cell, you will be damaging it too. I don't know what happened. You still see me? Sorry.
Yes, we do.
Yeah.
Because show up something different here. Sorry, just a second, see if I can fix it. You're seeing, what are you seeing, by the way?
You see the slide that's labeled 15.8, uncertainty, and you have some of the cells there, electro.
Okay, because for me, it's just disappeared and I'm seeing the Zoom showing me that I need to sign something for the Zoom app. Sorry, I will try to find where is my presentation for me.
Sure.
I'm in the dark now. So again. Bobby? No, it's showing the Zoom for me, not the presentation.
So
Oh, okay. So I will try to explain, and the point is that I can see. I'm really blind here. Just a moment. I don't stop video. No.
Usa setinha.
I'm gonna close this and see what happened. No, I'm blind. I can't see.
Maybe if you close the presentation, start again the PowerPoint.
Yeah, sorry. Yeah, maybe.
Stop sharing your screen and start over. I think that may do the trick.
Probably. Sorry again for all this. Let's start again. I don't know what happened. Okay, let's see. Now I'm back.
You're back. Good.
Thank you. Oof. And so just rephrase and get the point that I stopped. I think I stopped here when I was talking about the dye and the damage of the particle and the disposable cell. So if you use solutions that can damage the surface, or if you use metal deposition that can be deposited in the electrode, and also you have to check if the electrode outside the cell is not ruptured, because all of this can introduce this source of error in your measurement. And it seems a little bit odd, this information, but it happens. You have to be sure that you're using the correct cell for the measurement, because if you use the size types for the Zeta potential measurement, you won't be able to measure anything. So you have several types of cell to be used during the Zeta potential measurement. You have the disposable foldable capillary that when it gets old and you can't use anymore, you just trash it away. You can use the solvent resistant cells for specific types of the solvents, high concentration Zeta potential cell, and so on. One source of error, this one we did experimentally in the lab. We prepared silicon nanoparticles and we add some dust on it. And this dust is very clear in all types of the displaying, like electrophoretic mobility, Zeta potential, frequency, and phase plot as a sharp peak. And the sharp peak, it's meaning that we have a dust or something that is not good for your sample. One way to avoid this is, of course, try to work in a clean space. And also, if you have some doubts about your results, you can filter your sample to make sure that you are removing this dust from the sample. And finally, one thing that really is important, it's the way that you clean and fill your sample in the cell. Because if you don't do the correct cleaning process or the corrective filling process, or even let the bubbles inside the capillary, or also introduce yourself in the wrong way in the equipment, there is a correct orientation for this, you probably get wrong results and you have to redo your experiments. So in terms of perspective, this technique, it's a very simple one. Most of the calculations are done by the equipment software. So when we look at all the equations, you don't get to take a look very much on it, but you have to try to understand the results that you have. And it's wide open areas that can be used in this technique. So again, I think I lost my view. Sorry again. And the last one is just I don't know, I lost it again. Sorry. I have to put it back. I don't know what's going on. And
yeah, there you go.
Yeah, and of course, thank you all for the time, and I hope you enjoy even with all the interruptions. And we really, really have to thank you, all the supporting funding agents here in Brazil and in Canada for this work, and the Canadian Journal of Chemical Engineering for the opportunity to publish this series. And if you have any questions, I'll be glad to answer.
Thank you, Claure,
so
for
much.
an excellent overview of the Zeta potential technique. We are a little behind schedule, so we have time for one short question from the audience. It's not your fault, you had technical problems.
No, sorry for that. But we can talk in the chat later if someone has some questions. I'll be glad to answer. Thank you again.
Any questions from the audience? We do have time for one quick question, if there is any pressing question. Okay, so if not, thank you very much again. And
Thank you again.
we will move on to the next speaker. I think Dalma will introduce the next speaker.
Sorry, we have a question at.
Oh, we have a question. Okay, great. Who is asking the question?
No, you can, if you want. Wait 2 seconds.
Okay.
Okay.
We have a question. Do we have a question?
Yes, sorry. So I understand from your presentation that you can actually have neutral particles, but because of specific ion absorption, they will actually have either a negative or positive zeta potential. Is that correct?
Is that correct? Yeah, if you use a neutral particle, you won't be able to measure it. I'm quite sure if I understand your question. But if you have a positive or a negative one, you will be able to measure. So you can have a positive or negative values for zeta potential.
There you go. Okay, well, thank you very
Thank
much.
you so much.
And so Dalma, if you want to introduce the next
Yes,
speaker.
let's move to the next speaker. Please welcome Christopher Panaritis from Polytechnique Montréal, and he will be talking about the cyclic voltammetry.
Thank you for the introduction, Dalma. You hear me well? If you don't, if you do.
Yes, everything's okay.
Perfect.
I hear you well.
Perfect. Sounds good. So as she mentioned, today I'll discuss the experimental methods on chemical engineering on cyclic voltammetry, or CV for short, working with Professor Patience at Polytechnique Montreal. So to begin, I got it. Yeah. Thank you. Some highlights. Just to highlight on my talk, I'm going to first discuss electrochemistry. What is it, and how you apply the cyclic voltammetry technique and setup. CV for short is used, or cyclic voltammetry is used to characterize the oxidation and reduction properties of a conductive material. And then I'll go through the uncertainties of the reaction and of the process, and then just a couple of case studies on catalysis and one on spectral electrochemistry to discuss the perspectives and applications of it. So to start off, electrochemistry is the transfer of electrons through a process allowing the chemical change in the material. So in this example here, we have one container containing the zinc ion solution, ions, and while the other one containing a dissolved copper ion solution. And on the left, we have the zinc anode electrode deposit inside the liquid, while on the other side, we have a copper electrode. The copper electrode acts as the cathode, where reduction of the ions take place, while the zinc anode acts as the oxidation reaction, acts as the oxidation process. So zinc is broken down to zinc ions in the solution, and we apply a potential difference between the both anodes. We're able to send electrons from one end to the other, cycling from one side to the other. While this happens, as I mentioned, copper ions from the solution are reduced on the copper electrode, while ions are transferred, electrical charge is transferred through the salt bridge in between, which is not permeable to the copper and zinc ions, and then it reaches the zinc electrode, where oxidation takes place and closes the electrochemical circuit. So that's when just a brief overview and introduction of electrochemistry, summarized quickly as I can. And just now to introduce a 3-electrode cell. So a 3-electrode cell is needed for cyclic voltammetry experiments, CV experiments. So in this case, we need a working electrode, a counter electrode, and a reference electrode. The working electrode is the electrode of interest, where we want to measure its potential, where we want to control its potential difference, and this would change with, this determines the properties of the material. On the working electrode, it can be used as, just as I showed previously, a zinc or copper pure metal electrode, or some type of other species, or a catalyst can be deposited at the tip, and this could be induced through potential differences, and this could determine the redox and oxidation states of the catalyst. The counter electrode is used to close the electrochemical circuit, so ions are transferred from not ions, but electrons are transferred from the working to the counter electrode, while the reference electrode ensures that the potential reading of the working electrode is being read. If without a reference electrode, we will just have the potential difference between the counter and working, and this will not give us an accurate representation of the working electrode. And finally, the solution it's in is composed of electrolyte to ensure conductivity, and sometimes an analyte is dissolved in there for the process to take place, like the copper ions, as I mentioned before, or some other material. Let's say glycerol is in the solution. This can be oxidized or reduced with the catalyst. So what is a cyclic voltammetry? It's essentially, we're using the 3-electrode setup, and we apply a potential difference between the counter. We apply the difference at the working electrode, and we cycle it through a scan rate of millivolts per second. So it goes from one end of a bit lower potential to a higher potential, and up and down until as many cycles as required, and it generates a curve as shown here on the right, some sort of duck shape, as we say. So as we move from left to right in the process, from step 1 to step 4, we actually increase the scan rate. So in this example, we're going to have the analyte in the solution as X, that is oxidized from step 1. Let me just put a pointer. So as we go from step 1, the X ions in the solution are oxidized to X plus, and reaches a maximum at step 3. So this is the occurrence where the ions and the analyte is sent through the circuit and on the working electrode, and are oxidized on the electrode. And as the current increases, the diffusion layer forms around the electrode, and this reaches a maximum, while after that levels off at step 4. And then once we reach step 4, we reach the limit of the potential window, and we go backwards to reductions to reduce the species. So we reduce the X plus ions back into X plus back to X, and the cycle could be repeated as much as it can. And as the cycle is done for several steps, as many as required, you will end up with a reversible process if they overlap all the time. And of course, it's irreversible, and there's something different with the setup if it doesn't overlap. So there's a wide range of applications that this technique has been used in the last 2 years. Over 8,000 publications have cited cyclic voltammetry. And these are some of the main keywords that are associated with this finding. The first one, the top one, is supercapacitors or batteries, which makes sense since cyclic voltammetry could be used for batteries to learn their cyclic ability, so how much they can recharge and discharge in terms of and also include their current densities, so how much charge they can hold, and how much the lifetime of a battery could do through excessive cycling and discharging and charging again. The second point is catalysis. So this is the number 2 keyword cluster found, which is of course the catalyst, which is composed of the cyclic voltammetry is used to detect the oxidation state of the catalyst or the different states of the catalyst, and they're highly popular for water splitting and CO2 electro reduction processes and other various chemicals that you want to oxidize or reduce. And then finally, well, not finally, but we have the third application, which is sensors. So again, cyclic voltammetry could be used in sensors. For an example, you want to have a glucose monitoring for a diabetes patient or just a regular person, and they want to check their glucose levels. You can use cyclic voltammetry to determine at what potential this certain amount of glucose concentration is found. And then we know from using the sample, we're able to say, okay, if it's reached this potential, we can see how much concentration of glucose is in the system. Fourth point is on films and conductive material. And finally, metal organic frameworks or MOF, which is similar to catalysts, and the same ideas of redox properties can be determined. Before I dive into just perspective applications, I'll just quickly go over the uncertainties, just covering a few over here, but essentially, as long as the process is done in a clean environment and everything is the error from human error is very limited, this process should happen. So should be back and forth. It should be reliable and reversible. However, sometimes there is an ohmic drop that occurs. So the potential reading of the working electrode is not being read properly. So this can be corrected by moving the working electrode closer to the counter electrode, or even increasing the conductivity of the solution. Then there's issues of reproducibility and stability of the anode of the working electrode itself, or when the catalytic material is involved. This is usually just overuse of it. Maybe it falls off or degrades over time, and the reading is inaccurate. This could be corrected by cleaning the working electrode on an aluminum water mixture, where you're able to remove all the impurities on the surface of the electrode and have the process be used again. And in this case, you can reproduce it as many times as you want, or until this reproducibility stability degrades again. In addition to replacing it back in the solution, you'll need to sonicate it. And then finally, you can also add a CV pre-treatment before any reaction, before any characterization. So just a little quick perspective. This is actually part of my previous work where we replaced the liquid electrolyte solution with a solid electrolyte. In this case, it's called yttrium-stabilized zirconia, or YZ, which is an oxygen conducting solid electrolyte disc, where oxygen ions are able to move through the solid material. And so we're able to do electrocatalysis reactions, electrocatalytic reactions on it. So in this case, we analyzed an iron film deposited as the working electrode, a catalyst. On the opposite side, we deposited the counter electrode and the reference. And the setup looks as so. So we tested CO2 plus hydrogen over the reaction, over the catalyst iron. And once we apply a potential difference between the two electrodes, between the working and counter electrode, we're able to send oxygen ions to and away from the surface of the catalyst and control the oxidation state and reaction intermediates and binding energy of the reactant species. However, in this case, I won't go into the reaction details. I'll just go into the cyclic voltammetric application, where we had the reaction under CO2 and hydrogen 1-to-1 with a 20 millivolt per second scan rate at 350 degrees. We see this cyclic voltammogram being produced. So as we move from the left and negative potential to the positive potential, we oxidize the iron catalyst into Fe2O3. That once we go to the more extreme in the window, we actually induce oxygen evolution. So oxygen from the YZ electrolyte is just being sent out We don't want that. So then it's limits our window to this range. That when we return back, we reduce the catalyst back into its old form or into the reduced form. We go through 3 different stages where first Fe2O3 is reduced to Fe3O4, Fe3O4 to FeO, and then FeO to metallic iron, while the last step over here, CO2 electroreduction takes place. So even if there was no catalyst, or there was a catalyst, but CO2 could be split by itself at this range. However, why do we care? Because we don't want to go all the way to minus 1.5 and waste energy. So the cyclic voltammetry tells us, and through experimental findings, we find that iron Fe3O4 or stage 2 is more favorable. So with this idea, we're able to charge this catalyst at this potential difference, and this favors the reaction. And just a quick overview of the cyclic voltammetry different cycles. We see the step 1, the first cycle is represented by red, while cycles 9 to 10, or it should be 2 to 10, the last 9 are represented by the blue line. So essentially the cycle after the first cycle is very reproducible. And while the first cycle is inaccurate, since it just determines what the state before the material, we induce potential difference. So as we can use it for catalysis reactions specific to chemical engineering, and also we can use it as we can pair it up with spectral electrochemistry, where we use an infrared source to monitor the surface intermediate species that takes place on the electrode. So in this case, we're able to polarize the electrode and then see the absorption of intermediate species. And here the example on the right, where this example takes glycerol oxidation. So the oxidation of glycerol takes place as tested at different potentials. So as we increase the potential from 0.34 to 0.54, we're able to see these new peaks appear in the infrared spectra that are associated to new intermediate species, new reaction conditions that occurs at these potentials. Finally, we're just going to sum up that cyclic voltammetry is reliable and efficient method to characterize electrochemical material. It's an in situ technique to characterize the redox properties of many different reactions and processes, especially the processes that are electrochemically conductive and in terms of catalysis. And as I mentioned, it's useful for chemical engineers in catalysis, and if you want to in situ characterize the samples. Thank you.
Thank you very much, Chris. We have time for a very quick question from the audience.
Yes, we have a question here. So our question is, how can we tell that if it's strongly absorbed on the working electrode, or is it from the solution when we conduct the cyclic voltammetry? That you have to do it in different steps. So we have to test the different your hypothesis of what's absorbed. There's no way really to tell. You have to always have some reference. Right. So your question is, you could tell. Right, exactly. So you have the.
We cannot hear it. We cannot hear anything.
So the question is, how do you differentiate between an absorbed species if it doesn't diffuse back into the solution, right? And as it oxidizes or reduces in the solution, material in the solution, Does that make sense? So so that's what the catalysis is. So that's when we do the glycerol oxidation, the catalyst is deposited on, and so you're able to actually determine everything. As long as they don't overlap, you can see the oxidation state of the catalyst and also the solution change as well. Again, you will need to you have to do everything separate to really reference what process is occurring.
Okay, thank you very much.
Thank you. There you go. Or is it done? Next person.
Yes. I'll let Professor Suarez introduce the next speaker if he wants to.
Thank you, Donna.
Yes.
The next speaker is Nooshin Kazeroni, and I'm sorry if I mispronounce her name, and she'll be talking about methods to measure pH. Welcome, Nooshin.
Thank you, Professor Suarez. Can you hear me?
Yes, very well.
Okay, good afternoon, everyone, and welcome to my presentation. The experimental method that I want to talk about is pH. Everyone might think that measuring pH is an easy and reliable job with conventional methods, but it's not always the case. So today I want to talk about glass pros that dominate R&D, emerging techniques, including ISFETs, imaging optical fibers and spectroscopy, and uncertainty and sources of error that might occur during pH measurements and during the experiments with a glass electrode. The standard deviation approaches 0.1%, but frequent calibration was required. And Web of Science indexed 20,000 articles in 2020, which indicates the importance of pH. So the history of pH goes back to 1909 when it was introduced, and now it is defined as the minus logarithmic of activity of hydrogen ion. Here you see a typical pH scale and with some examples. And here one important range in this scale is the biological range, which you can see in this picture. And here you can see that for some organs of the body, the range of pH is very narrow, so accurate pH measurements is very important. So the most conventional measurement for pH is glass electrodes, which probably everyone has used. It consists of a silver and silver chloride electrode immersed in a potassium chloride solution, and the reference system is in the outer tube. So the heart of the glass electrode is the pH sensitive glass, which is called the membrane. If we take a closer look here, when the pH is immersed in a solution, the hydrogen ions penetrate through the membrane, and the same occurs inside the membrane where we have a neutral pH buffer. And the extent of charges in the inside is proportional to the concentration of hydrogen ions in the solution, and this creates a difference in voltage, which through Nernst equation, pH is determined. For applications that very small samples are required and where we need fast response of the pH sensor, we use ISFETs, which are alternative to glass electrodes. These ion-sensitive field effect transistors are also potentiometric techniques, and they use the same technology as in your laptops and in your smartphones. And here there is a pH-sensitive layer between these sources and the drain, and in the ISFET gate. And this pH-sensitive layer interacts with the hydrogen ions in the solution, and this creates an electrical current between source and drain. And the strength of this electrical current is what identifies the pH. Next, we have optical fiber probes, which make possible remote sensing of pH, and also it can be used for small volumes of samples. Here, the principle is that the light is passed through a light guide, and then it interacts with pH-sensitive dyes, and the pH-sensitive dyes alter the intensity of the light that goes out to the detector, and pH is measured. So here, remote sensing of pH is possible because the light can go over long distances, and one important advantage of this technique is that, unlike the other two previously mentioned methods, there is no electrostatic or electromagnetic fields, so it can be used for in vivo applications. Here is a bibliographic map of the applications of pH in that Web of Science has indexed. And here you see the red cluster, which has the most keywords, and the most mentioned keyword is mechanism, optimization, and separation. Here is the green cluster, and degradation and oxidation are the most mentioned keywords. For the blue cluster, kinetics is the most mentioned keywords, which indicates the importance of pH in chemistry and chemical engineering. And for the yellow cluster, heavy metals, sorption, and equilibrium are the most mentioned. And finally, for the magenta cluster, nanoparticles are the most mentioned keyword. Several sources of error might affect the accurate pH measurements. For example, calibration. The pH measurements are only as good as the calibration, and if the calibration is done improperly, inaccurate pH values are obtained. And one important factor that affects pH is temperature. And here to indicate the effect of temperature on the pH, we conducted experiments with 3 samples, MgSO4, NaCl, and 1 acetate buffer. And we increased the temperature. As you can see, the pH decreases as the temperature increases, which is confirms the Nernst equation. The temperature has 2 main effects on pH. One is in the change of equilibrium and dissociation of a hydrogen ion, and the second is on the voltage that is induced by the pH sensor. So as we get further from the calibration temperature, the error increases. Aside from environmental conditions like temperature, pressure, and electrical fields, there are also chemicals in the samples that might cause error. For example, biofilms, greases, proteins, and solids might create a coating that prevents efficient contact between the electrode and the solution. So this may cause error. Also, some samples like chelating agents, hydrofluoric, and alcohol in the reference electrode, and some special samples that are abrasive, for example, that can damage the electrode, or low conductivity where there are no sufficient ions to transfer the voltage, and for highly acidic and basic solutions. For the future directions, the first thing is miniaturization. Miniaturization is important for applications that in situ measurements are required, like in biomedical applications, and for example, in cell culture. And because currently the glass electrodes that are commercially available, they do have dimensions that does not allow the direct use of the pH sensor in the sample. So the next emerging technology is a spectroscopy, which is being used in biomedical applications like oncology. And the concept is that to determine the pH of an unknown solution, some small amounts of pH indicators are added to the sample, and then the dissociation of these indicators indicates the pH. And there's wearable sensors. For example, these sensors are rapidly growing in markets, so they are used for online monitoring of health and body activities, and it is necessary to develop wearable sensors for measure the pH of sweat of body, for example. And also, there is a need to upgrade from invasive techniques to non-invasive techniques. For example, when we want to talk about cell culture or biomedical applications, or for example, in microreactors where the existence of a pH meter alters the conditions in the reactor, it is necessary to develop non-invasive techniques. So to wrap up, glass electrodes still dominate R&D despite their shortages. Biomedical applications require invasive, in vivo, and non-invasive probes. Emerging techniques are ISPET, optical fibers, and spectroscopy. The standard deviation for glass electrodes approaches 0.1%, but frequent calibration was required. And to show the importance of pH, we saw that Web of Science indexed 20,000 articles only in 2020 that mentioned pH as a keyword. Thank you.
Thank you very much, and for this excellent overview and for teaching us that pH is much more complex than most of us realize. It's very nice. I don't have a question for you, but I do have a comment. I think if I recall well, I think this morning I accepted the pH paper for the Canadian Journal, the revised version. So if you have not received the email yet, you should be receiving it soon. So good news.
Yes, I received it this morning and I'm very delighted. Thank you.
Good, excellent. Congratulations. All right.
Thank you.
Any questions from the audience?
I do have a question.
Yes.
So Nooshin, you're talking about all these electrodes, and when we talk about measuring acidity, normally we are in aqueous diluted solutions. So what if we are in concentrated solution, like for example, ionic liquids, and I want to determine the acidity? Would I be able to use the same electrodes? For example, for determining the, I don't know, like Hammett acidity. Like, would I be able to measure the acidity of a conjugated acid of a weak base with the same electrodes?
You mean in cases of high concentration or highly acidic?
Both.
For higher concentrations, we did some experiments, and when the concentration was very high, the pH electrode, which was a glass electrode, started to drift, and it didn't show the exact value. And also for highly acidic and alkaline solutions, there's a alkaline error that occurs during pH measurement with glass electrodes. So I don't think glass electrodes that are normally available in laboratories are the best choice for these solutions.
Okay, thank you.
Thank you.
I guess we can move to the next speaker. Nooshin, can you please stop sharing? Thank you.
Thank you.
The next speaker is Professor Abdellah Aji from Polytechnique Montréal, and he will be presenting barrier properties. The floor is yours.
Okay. Good afternoon, everyone. So do you see my screen?
Yes, we see it.
Yep.
Perfect.
Okay, good. Okay, good afternoon. So this last presentation will be on the experimental methods in chemical engineering, barrier properties. So it is about the barrier that measure permeation properties to various gases in particular. So okay, So why the barrier properties are important? Because in many applications, such as packaging, for which permeation to gas, oxygen, water vapor, or other CO2, for example, are important to control or monitor, because they have a significant impact on the shelf life of a product. It can be a food product. It can be also electronic packaging that are sensitive to oxygen or to moisture or water vapor, or other types of product. Plastics in particular, and this is, I will talk mainly about polymers and plastics, because are among the materials that are used for these packaging applications, and that have some wide range of permeation and barrier properties, from quite permeable to quite impermeable. And also they are used, as I mentioned, in many food packaging applications, for example. So knowledge of the permeability characteristics of polymers is important. So in the case of polymers, the permeability to a gas is controlled, of course, both by the polymer structure, so chemical nature, etc., and the gas that will permeate through it. So free volume, for those of you who are familiar with polymers, there is one quantity, one property of a polymer that is chemical nature. So what are the chemical groups that are in the main backbone of the polymer, and it affects this free volume. If that free volume is large, then permeation to certain gases will be large. If it is small, the permeation will be small. So this is affected by the nature of molecules. Crystallinity also is important. But crystallinity of crystal is a perfect structure, so there is no permeation in a crystalline phase. Whatever it is, a metal, a glass, or a polymer, the crystalline phase is impermeable. So the permeation happened only for polymers in the amorphous phase, or at the interface between amorphous and crystalline phases. So the permeability also is affected by hydrogen bonding, so the polarity of the polymer will have a certain importance, and environmental conditions, temperature, pressure, etc. So from the permeant or the gas side, of course, the size, when you have a large or small gas molecule, its permeation will vary, will be different, or will affect its permeability in a certain material. And also, as we will see, because the permeability is not just diffusion, it is a combination of this diffusion and solubility. So desorption and desorption of gas molecules into the polymer will also play a certain role in permeability. So if you take, this is just a sketch that shows you have a membrane or a film or a sheet of a polymer, and you have a gas at concentration C1 and C2 with a partial pressure P1 and P2. And then, of course, because of thermodynamics, you will have diffusion from one side to the other if the gas can go through. So it needs to first absorb or be solubilized in the material, diffuse through the material, and desorb from the material. So, and then at steady state, at a certain, when you reach steady state, then you will reach a certain level of concentration C1 and concentration C2. So if you look into the, at steady state, into the amount of material that permeated through, or the flow rate permeated through this membrane, you can write it as, well, F is minus D, diffusion coefficient, and the gradients of concentration through your membrane. And you see that this, if you use, for example, Henry's law, and the relationship between partial pressure and concentration, then you can write it in the form that is in here. So as the product of diffusion coefficient and solubility that appears here from the combination of Henry's law and the gas, the relationship between concentration and pressure. And L here designate the thickness of your material. So it is, the permeability is defined as the product, the DS. So P is permeability of a material, is the product of diffusion coefficients multiplied by the solubility coefficients. And if you designate by Q the amount of material that's diffused through a certain surface A at a time t, then this permeability, if you use this equation here, can be written as Q L thickness divided by A surface time and delta P the pressure. And the units, for those of you who work in this area, there is a variety of units that are used. The SE units, of course, are kilograms, meters divided by square meters, seconds, and pascals. But we do have many other types of units. The one that is mostly used in packaging are cubic centimeters multiplied by mil. So a mil is 25 microns divided by square meters day atmosphere. Or sometimes instead of using mil, we use micron. But this one, cubic centimeters mil by square meter day atmosphere, is the one that is mostly used in packaging. So there are also some other quantities of interest in permeation. One of them is permeance R, which is the permeability divided by thickness. So, or it is also, if you express it from the previous relation, it will be Q, the amount of gas divided by surface, time, and delta P. Or another one that is also used, you are familiar probably, water, WVTR, which is water vapor transmission rate, or in general for any gas, the gas transmission rate. And this is defined here as this pressure, the differential pressure multiplied by permeability divided by thickness. Or if you again use the relationship, the definition of permeability, it will be the amount of gas that permeated divided by surface multiplied by time in here. So this quantity and the permeability property are the ones that are mostly used. So in terms of experimental techniques that are used to measure permeability, there are mainly two types of techniques. One that is called the isostatic, and one quasi-isostatic. Those of you who are familiar with those type of equipment, there's one from the company Mohini in the US for oxygen permeability, for example, this is Oxtron equipment. And they work basically for the isostatic method as, so you have a cell, so isolated cell, in which you will permeate, you will have a gas at a certain concentration or a certain partial pressure, P2, coming in, and then you have your film, the gas will permeate through the film, and you have a carrier gas on the other side. Initially, you start at the pressure, partial pressure. No, so the partial pressure here in this case is always zero because the carrier gas will remove the permeated gas all the time. And that will go to a detector that will detect the concentration of that gas in the carrier gas. So at steady state, that concentration will be constant. So this is the quasi-static. So the partial pressure here is always pressure for that gas. So if you know, for example, if you have like atmospheric air for oxygen, then you will have always 0.21, which is the concentration of gas that you can translate into 0.21 atmospheres, and here it is 0. For the quasi-isostatic method, we don't have a carrier gas that removes the permeated gas through the membrane. So it accumulates. You have here always permeance that accumulates and its concentration increases with time. So you have a sensor here that will measure the concentration of the gas as a function of time. So, and in terms of representation, so for the isostatic method, so you have this, if you represent the rate, so the volume divided by time or the flow rate, as a function of time, you have this type of curve in which you reach at steady state to constant flow rate, to constant concentration of gas and flow rate that you have here. So if it is, we call it RSS, then your permeability P will be RSS L divided by A delta P. So RSS is just basically the amount Q divided by time, and you have the permeability definition. And you can also, you can derive the diffusion coefficients from the half time that is designated here in the curve. For the quasi-isostatic method, in which you have a constant increase of permeant gas, then it is the slope, that is the RSS is the slope, and it represents the same time. Since you have Q and here time, so the slope will be Q divided by T. And the permeability is this RSS L divided by A delta P, and in the diffusion coefficient is determined using the theta, that is the value in the abscissa here. So now, what are the factors affecting permeability? As I've mentioned, polymer chemical structure, of course, is important. So polarity, stiffness, lateral groups, or the size of lateral groups. We will see a table in the next slide. And also, of course, the chemical nature of structure of the diffusing molecule. So if we look into the polymer itself, so if you have the lateral, so the side group that you have in the main backbone, so these are permeabilities to oxygen. So polyethylene is just hydrogen. So you have permeabilities here in cubic centimeters, mil, square meters, day, atmosphere. So, and polyethylene is non-polar. So you have generally, polyethylenes are highly permeable to oxygen. But if you go to some polar materials like PVOH, so you have OH here, as a lateral group, you see the value is quite small. So because of interaction between oxygen and the OH, then it's like retards or hinder the diffusion of oxygen through this polymer. If you have a large group, for example, that are non-polar, like in this case, so you have a PMP, you have even higher permeabilities than for hydrogen. So, and so on. You can find these for different polymers in tabulated in tables in various textbooks. For gas effect, so as in general, as the molecule is small, the permeability will be higher. But if the polarity, if you have also some polarity, then it can affect the permeation. So if you compare here, you have nitrogen, oxygen, CO2, and you have the values for all these molecules. You have the molar mass, the polar, non-polar, and the permeability to the power 10 minus 10 to the 10, so cubic centimeters. In this case, it is centimeter instead of mils or microns. And you also can find sometimes what we call relative permeability, which is defined with respect to nitrogen. So if you know the permeation of your membrane or your polymer to nitrogen, then you can deduct or calculate its permeability to various other gases using this ratio. So this is the ratio of permeability to a certain gas. For oxygen, for example, it is 3.8 times more than for nitrogen, for CO2, 24 times more, etc. The effects of temperature, it is very important. So it follows basically Arrhenius type of dependence, because the permeability is the product, as I mentioned, of diffusion and solubility. So just your activation energy will be a combination of the activation energy associated with diffusion and solubility. So, and it has some similar relationship. You can also find tables in reference books in which you have this activation energy and the permeability at a certain reference temperature. Effective relative humidity, so it affects particularly, you see, for EVOH, for example, or polyamide nylons in a dry state and in 100% relative humidity. You see for EVOH, for example, with 32% ethylene, it is 100 times more, almost 2 orders of magnitude higher in moist atmosphere, and nylon it is about probably 3 or 4 times more than it is in the dry state. So this is particularly important because these are the polymers which are the most impermeable to water vapor. The only polymer that is not sensitive or less sensitive to water vapor is PVDC, polydivinyl chloride, which has also very good barrier to oxygen, but it is now almost discontinued because of the presence of chlorine and the difficulties associated with its processing and recycling. So it is less and less used. Crystallinity, as I mentioned, it will reduce permeability as well as orientation. Orientation is also another process or additional processing operation that we can induce that will reduce permeability. And you see here, for example, for polypropylene, oxygen transmission rate as a function of draw ratio, how much you draw on a polypropylene film, and you see a continuous decrease as a function of draw ratio. So finally, just a word about multi-layer structures. As you know, in packaging, we use, well, from now we are trying to find other solutions because this is an issue for recycling. But for a long time, multi-layer structures that combine different materials for a certain function. If we need barrier to oxygen, barrier to water vapor, and we want a seal layer, we want an abuse layer, etc., then usually it is a combination of all those structures. So if if you write your partial pressure for a certain gas, and it is P1 on one side and P2 on the other, and of course you have the partial pressure through different layers, which is additive. So if you go back to the permeability coefficient, you will find out it is just like it is a parallel model. So you can have your total permeability as the total thickness divided by the summation of the relative thicknesses of each layer divided by the permeability of each layer. So you can calculate the total permeability in this way. So this summarizes basically what I've said about the barrier properties and permeability in particular. So it is relatively simple to measure and interpret. Applications of the permeability equation is quite useful for those working in packaging in particular. You can calculate what is the shelf life of your product. You can calculate what are the condition of environmental condition effect on the quality of your product, etc. So there are many uses that can be done, and complex material structures can be designed for various applications. And thank you for attention. I will be happy to answer any question.
Thank you very much, Professor Aji. Do we have questions from the audience? Otherwise, I do have a curiosity. I don't see questions from the audience. Okay, I do have a question myself. Thank you for the presentation. It was very insightful. It is actually the first time that I see how to measure the barrier properties, so permeability. So that was very interesting. One question, when you showed the setup that you use to measure permeability, I saw that there is a detector. I was wondering what type of detector is normally connected to the instrument.
Well, to be frank, because these are equipment that are sold by companies, and each company has its own technology. So sometimes they will disclose what type of detectors they use. Sometimes they will not disclose. They can be electrochemical detectors. They can be, I know we use, for example, we have separately, because we have also some oxygen detectors that we can put in any environments and seal it and follow from outside. Of course, if it is transparent, the evolution of oxygen content. This is particularly important for oxygen scavenging materials. In that case, it is an electrochemical detector that you shine with lights, and then you have some interaction and you have a reading of the oxygen content. But the exact type, I don't know. The companies.
Okay. I was perfect. Electrochemical. I was just curious, so that answers my question. Thank you.
Okay.
We technically should have another presentation by Professor Anderson Gomes, but he's not here, so I don't know if he's still having technical problems. And so I don't see him. And he hasn't replied to the email. So I think he's still having technical problems. So I think we can conclude today's experimental method symposium. Thank you for all presenters. I know in Palais de Congrès, a lot of people are attending in person. So I hope you guys there enjoyed. And see you, perfect. Adrian is there. Thank you very much. And we'll start again tomorrow morning at 8:15. Thank you very much, Professor Suarez, for co-chairing this symposium with me today.
My pleasure, Abdellah. You did a great job, and thanks to all the presenters this afternoon and of today. Thanks.
Thank you very much. Goodbye, everyone.
Thank you. Bye-bye.